afternoon. So this is work done together with Carsten and Manita. And I hope you remember the lecture by Carsten on Monday, because today I will show mainly applications of ray tracing theory and the scattering integral. So I won't go into the details of the derivations of the theory, as I hope you remember. I also will talk about this recent published paper of us, which is on the evolution of internal gravity waves in a mesoscale eddy. So, okay. Okay, now. I'll motivate the research question with this space-time diagram here on the right. It shows the different dynamical regimes in the ocean with these pink bubbles. They come from the largest ones to the smaller ones. And it also shows some dispersion relations. We will focus here on the internal gravity waves, which live between F and N. This can integrate with, interact, sorry, oh, this is not loading, okay. This can interact with a background flow, like some eddy field, or with other waves, which don't load as well. Okay, slowly. Anyways, there are some arrows pointing to smaller scales. So with these interactions, the scales of internal gravity waves are supposed to get smaller, such that the waves become eventually unstable and break. And so in this process, they transfer some energy into the beautiful arrows to the turbulent regime, where they will induce mixing across densities, and so increase the potential energy of the flow and connect. There is supposed to be an arrow here connecting the smaller scales with the larger ones. Now, models nowadays are shown here by these gray boxes. They don't cover the whole domain, and therefore we need to parametrize these interactions. They don't cover the whole domain because they use some kind of filtering time and space, like a Reynolds average. So to parameterize this interaction correctly, we need to understand the energy transfers better, and that is what we are trying to do. Okay. So the first part of the talk will be on the interactions of internal gravity waves with a field of eddies. And for that, we will use just like a traditional kind of ray tracing approach that Carsten already introduced on Monday, using the VKB approximation. So all the waves that we'll study are smaller than the eddies. Okay? And then you can derive some kind of like the dispersion relation here for the internal gravity waves, which this is the frequency of encounter, which fills the Doppler shift. Now you take some derivatives of this dispersion relation or the frequency, and then you get here the ray equations. Okay. So I will do a few experiments. The first one would be just shooting some rays into a random eddy field, which is initially, well, it's balanced. It will stay stationary throughout the simulation. Here I'm showing the speed of the eddy field, and it's barotropic, and also the stratification is constant throughout all the domain. I initialize all the rays over here is 25 rays, all of them with the same initial wave number, and I shoot them in the eddy field. So, well, they are propagating up and down, no? Reflecting at the ocean surface and the bottom, and being refracted and spread in the domain. So if we look at this evolution in phase space, here I show the three-dimensional phase space. The cone represents the constant frequency cone where I initialize my rays. On this, I hope you see, there's a red dot there. All the waves are initialized there. And by the end of the simulation, they spread horizontally in phase space. So the eddy field is isotropicizing the wave field in horizontal wave angle. Now we do the same kind of experiment, but for a baroclinic eddy field, where I have like the first vertical mode, so there is some shear in the vertical. We see that the rays they follow different paths, as the vertical wave number is also changing in the simulation. And what we see is that there is a diffusion along the constant frequency cone. So while the horizontal wave number and the vertical wave number are both changing, the frequency of the waves stays the same. Now, these are actually quite large waves relatively from within the wave field, but what happens to higher modes? Well, when we go just in this, I initialize some rays in the same frequency, but with higher modes, And so we see that these actually fill the mean flow more, and they are refracted across frequencies. This you can think of as some kind of a critical layer where the frequency goes towards F, the vertical wave number shoots up, and then the waves become unstable and break. Now here we're doing just only a few wave rays, but we want to make a statement about the whole spectrum. So for that, we developed a novel numerical model, which is the internal wave energy model that Carsten already mentioned on Monday. It's based on the radiative transfer equation, which is 7-dimensional. It's a prognostic equation that explains the evolutions of here this epsilon is the energy density spectrum. So it's changes in time, explains changes in physical space, like advection. These are the ray equations here, X dot, Z dot. Also the changes in phase space by refraction. And then on the right-hand side, we have sources or sinks of wave energy, which are external from the wave field, and also the wave mean flow interaction, which is like a mechanical energy that the wave gather along the wave path. So they can take energy from the mean flow or give energy back to the mean flow. It can go in both directions, can have both signs. Okay? Now we will do simulations solving for this equation for one specific area and see how the spectrum of the wave field is evolving. We don't consider any sources of energy, so these are spin-down simulations, and we will consider only one sink of energy, which we relate to wave breaking by wave refraction. And this I try to explain with this sketch here. This is an attempt to represent 6 dimensions. So we have the physical space, X, Y, and Z. We have for the Z direction rigid lit approximation at the ocean surface and at the bottom, such that waves are reflecting. Horizontally, there are open boundaries, so waves are freely to propagate out of the domain. And then in each physical point in space, we have a full description of the phase space, which is shown here by this blue arrow. So you have here Ky, Kx, Kz. We define the phase space within the cutoff wave numbers. So all the waves that are large, have larger wave numbers than this cutoff, we assume that they are unstable and are prone to break. So you can imagine now if there is some strong vertical shear in the mean flow, the waves propagate towards a critical layer. Here the vertical wave number is increasing, in theory to infinity. During this process, they will cross here the vertical wave number cutoff. And there we can measure the energy flux going out of the domain in phase space. And when we have measured that, we can just plug it in the Osborne-Cox relation and infer diffusivities, assuming a mixing efficiency of 0.2. Yeah. We do that for the horizontal as well. So now I will go into the simulation. It's based on observations of a cyclonic eddy, which we captured in the coast of Mauritania. This is the eddy. But we represent it in idealized ways, like a Rankine vortex, which I show here on the left. So it has a linear decay of velocities between the eddy rims, largest velocities at the rim, and then an exponential decay outwards of the eddy. The vertical structure is the first baroclinic mode. Also measured was here the stratification, like a profile, which we will take as horizontally homogeneous, but depth varying. And we just apply some smoothing and fit an exponential function to it. Now the speed of the eddy as well as the stratification will be stationary throughout the whole simulation. It's a 6-day simulation, but the wave field will change as it's interacting with the eddy. And that's what I'm showing here in the center. This is an animation that I will play just in a minute. Here I'm integrating the wave energy densities in phase space. It's VKB scale, so it's showing the wave energy. The wave energies in physical space across the eddy. And it's a logarithmic plot. Okay, so it runs for 6 days, and by the end of the simulation, we will see that at the rim, the energies have decayed the most, while at the center of the eddy, they are still quite large. Now we can explain this evolution by looking at each term in the radiative transfer equation, and we can start with the lateral wave mean flow interaction. So here I'm showing the total energy change due to the lateral wave mean flow interaction. So it's integrated in phase space and in time, and I plot it over the eddy, like from the top, and from a cross section of the eddy. So the lateral wave mean flow interaction is mainly governed by this equation here. So it's the changes of the frequency horizontally. Now we can reescribe this equation as with a dependency on the wave angle, and we get this expression here. And now we see that it depends on these shears of the mean flow. So depending where you are in the mean flow, you will have a different shear. Now this term here is shown here by these contour lines. And what we see is that at the center, the lateral wave mean flow interaction vanishes, but outside is positive, therefore the waves are gaining energy from the mean flow. And that is actually what we can see. If we plug in the conditions from the shears in this equation, at the center, the omega dot H vanishes, but at the rim or outside, it doesn't, as you have this condition. Now, this is not the whole story, as we have here a cosine phi sine phi, which if you integrate over 0 to 2 pi, will integrate to 0. So first of all, you have to generate some kind of anisotropy in the horizontal spectrum such that it actually doesn't integrate to 0. And I will explain that in a minute, but first, let's take a look at the vertical wave mean flow interaction, which shows mainly an energy loss across the eddy concentrated at the eddy rim. This is governed by this equation, so it's the vertical shear in the mean flow that is governing this energy loss. And we can think about wave action conservation if we know that in wave action has to be conserved. So if a wave is propagating towards a critical layer, means so wave action is energy over frequency. So the initial wave action should equal the one at the end, where the frequency of the wave should equal the Coriolis frequency, and therefore the energy has to decay. So we can say that all the waves that are propagating towards a critical layer will lose energy to the mean flow during this propagation. Now I mentioned that we have to develop horizontal anisotropy so that we can have some lateral wave mean flow interaction. And I'll try to explain this with the horizontal refraction. So here I'm showing, this is just the GM spectrum, is integrated over KZ and Z at a specific position in X and Y. This is just at the initial time of the simulation, therefore the GM spectrum is the same everywhere across the eddy. It's just showing here the inertial peak and then the decay with -2 in phase space. So this is Kx and Ky. Now, after 6 days of simulations, we get at the center the picture here in B, and at the northern rim this, and eastern rim this. So we see that at the eddy center, the refraction shown, horizontal refraction shown here by these arrows, which is described by this equation, describes a perfect circle. Therefore, the energies are refracted in a circular motion. Therefore, the isotropy, the initial isotropy in the spectrum is not lost throughout the simulation. However, if we go to the northern rim, then the horizontal refraction looks like this. And so the initial circle is refracted towards an ellipse that is oriented in the north-south axis, pointing towards the center of the eddy. The same happens at the rim, just pointing from the west to east towards the center of the eddy. And so we see that here, this kind of ellipse is slightly tilted from the main axis. And so when you integrate cosine phi sine phi with this perturbation, it doesn't integrate to 0. If the ellipse would be exactly aligned with the north-south axis, then it actually would integrate to 0, and we wouldn't have horizontal wave mean flow interaction. So this anisotropy is generated first by the breaking of waves due to the vertical refraction. Now, the vertical refraction is related, the argument is similar to a critical layer. A critical layer is just a very special case where you only have vertical shear in the mean flow. Here, this is an eddy, so we have also horizontal shears, but the argument is the same. Here we are located now at the northern eddy rim, where the mean flow has this vertical shear. The stratification changes like this in the vertical. So the waves that are propagating northward and southward are not filling the mean flow. So they are trapped in a cyclostationarity, and therefore the waves that are propagating down the water column and then up, so this is the vertical wave number, this is depth, they are trapped in a cyclostationarity where the energy that is given, that is lost, will be gained back again. So they cannot break. If you go to the eastward or westward propagating waves, these are filling this shear in the mean flow, and so the vertical refraction will will cause them to increase in vertical number. The vertical scales become small, and so they break. You can imagine here a wave that is propagating down the water column, then up. And in the upward propagation, Kz dot is refracting the wave to smaller vertical wave numbers. It will eventually cross the boundary and so becomes unstable and breaks. Now well, the question is, how are these energy changes actually, are these relevant? And for that, I compare local energy changes against global energy changes. So here is, this is physical space across the area from the top is integrated in the vertical in depth. And I'm showing the percentage of energy that is changed throughout the simulation compared to the initial energy. So these are the terms: tendency, propagation, wave inflow, interaction, and dissipation. And we see that locally there can be up to 50% of the energy of the wave field that is changed, even with a gain of energy due to wave inflow interaction. Now we integrate over the whole domain, we get these percentages here, where the wave inflow interaction horizontally adds up to a 7% of energy gain. All the rest lead to an energy loss. But what does this mean then for the eddy? The eddy is actually much more energetic than the waves, so it actually...
Energy loss by wave propagation?
By wave propagation, this is basically this picture here. It's the waves propagating out of the domain horizontally.
Where is that energy going? I can understand how it loses energy by interaction.
Yeah, so it's just out of the domain. You can imagine you have an eddy, and then the wave is inside the eddy. This wave can move out of the eddy and then will be lost. It's somewhere else. So this is a loss. We have the same simulations with cyclic boundaries, but then it doesn't change the percentages. Okay? So I was saying that the eddy is much more energetic than the wave. So actually these energy changes that add up to locally to a 50% of the energy of the wave actually causes less than 1% of energy change for the eddy. So we can actually say that that's one small step for the mean flow, but one giant leap for the waves. Now, we computed the energy loss by vertical wave refraction due to critical layers, and so we measure these flags and we can infer diffusivities. The diffusivities that I'm showing here, these are just a snapshot at the end of the simulation, and these sum up to an order of magnitude of 10 to the minus 7 meters squared per second. This is quite low compared to the Mann-Kabisal recipe estimates, which are 10 to the minus 5. But throughout the whole simulation, we actually observe values that range from 10 to the minus 7 to 10 to the minus 5. So just by this dissipation of energy, wave energy by vertical refraction, we are able to get such high diffusivities. Now, this is all good and well, but we wanted to make sure that we are kind of modeling something real. So we compared our simulations to observations. We deployed a mooring at the eddy center, and then with time, the eddy was propagating westwards. So at the end of the time series, we had measurements at the eddy rim. I show here the observations are the golden line for the eddy center, the silver line for the eddy rim. These are horizontal kinetic energies. So these are quite similar, right? The rim and the eddy from the observations, but we can actually show statistically that the energies at the center are 1.2 larger over all frequencies compared to the ones at the rim. And that's actually what we are able to simulate as well. The simulations are shown here by these dotted lines, the red one for the center and the green one for the rim. Of course, there are many differences, like there are no tidal peaks in our simulations, or this energy difference is much larger. So, of course, we are aware of our limitation. It's a BKB approximation. It's a linear system. We are not having any wave-wave interaction, nonlinear interactions, and we are not including tidal forcing, for example, or waves that are comparable to the mean flow. So we are suggesting that these differences are related to these limitations that we have. Now, I want to make just a final remark on my research right now, which is on nonlinear interactions, as we want to overcome these differences in the model. And for now, I'm focusing on wave-wave interactions. There is extensive literature. I just point here some of them, as I'm following more closely the derivation of the scattering integral as they do. And during my research stay in the last summer at Scripps with Bill Young, we figured, well, when we solve the linear system, the 3D business system of equations, we get, of course, the classical internal gravity waves with the dispersion relation, but also two special solutions for pure inertial waves or oscillations and pure buoyancy oscillations. So now this hasn't been considered in the scattering integral as far as I know, and we want to know what are the relevance of this. So we reevaluate the scattering integral following Carsten's derivations 2019, and we get to this picture. So here I'm showing the energy change. This is the content energy spectrum of the energy change due to wave-wave interactions, shown against KH and KZ in a logarithmic plot. This is the positive part, and this is the negative one. So here all this energy that you see here is going out of these wave numbers and going into this plot here, basically. And we see that, well, the pattern is quite similar. Still, there is much more values. It's also the amplitude is higher. So actually, we are seeing that it increases the energy change by 1 to 2 orders of magnitude. This I'm showing here resonant and non-resonant interactions, all possible interactions. So the question is this actually relevant? Can we see it in other simulations? And what about the resonant interactions? That is the ongoing work right now. So let me wrap up. So internal gravity wave rate tracing is a powerful method to model internal gravity waves in a stationary mean flow. If we have a barotropic eddy field, I showed that we have an isotropization of the wave field in horizontal space. And if we have a baroclinic eddy field, then there is a diffusion along the cone if we are looking at big enough waves. Now, we developed IBEM, a novel numerical model, spectral model, to assess the evolution of internal gravity wave spectra in an eddy, or any kind of situation is fairly easy to use and to adapt to different scenarios. But it is useful to evaluate the evolution of the whole spectrum and also to infer the diffusivities or the induced mixing. In our simulations, I have shown that there is enhanced wave dissipation due to vertical refraction at the eddy rim compared to the center, and that the wave breaking by vertical refraction is a possible explanation for enhanced near-surface mixing at the eddy rim. Of course, we are aware of our limitations, and although the ray tracing is a powerful and valid method for many realistic scenarios, the limitations of a priori scale separation can cause a problem, and therefore we want to go to the scattering integral and reevaluate the nonlinear interactions, also for the resonant and non-resonant wave-wave and wave-eddy interactions, including these special cases of pure inertial oscillations and buoyancy oscillations. Thank you very much.
Okay, thank you very much, Pablo. Other questions from the students?
Hi, can you hear me now? Good. So just a quick question. You talked on the last slide about how ray tracing is limited by the fact that it doesn't take into account scattering because it assumes an a priori scale separation of waves and mean flow. Now, if you go back to build off of Jim's question about wave propagation. So when you were talking about waves basically propagating out of the model domain and carrying energy away with them, and your domain box was basically centered on this eddy, right? So outside the box, the eddy isn't there anymore, correct?
Outside of the what?
Outside of the, so if you've got your model domain box and that's centered on this eddy, so this is where the eddy is, and the eddy isn't extending off the box, right? So
the eddy is always inside the box. Always inside.
So I'm not sure how these two play together, because when we assume that there's a scale separation, and when we look at, for example, the non-acceleration theorem that Carsten had spoken about, we have this idea that the waves as rays are going, they're being reflected back and forth off of the two interfaces in a region where the mean flow is homogeneous. But you're finding, using a ray tracing approach, that the waves are leaving this region. And presumably when you leave the eddy, U is is different. So if you're going up and you interact with the eddy, and when you're coming down, you've left the box, you're outside, then the non-acceleration theorem won't hold anymore, right? Because the energy losses on these two branches would be different. So I'm just not quite clear how you can have propagation outside being a loss of energy if you have a scale separation.
Well, it's just a wave that is, the scale separation comes as the wave is smaller than the eddy, right?
Right.
That's it. And if it goes out of the domain, it's like, I mean, you could do a domain slightly larger, and then the wave, you would still see the wave propagating out.
Right.
But here it's just cut it. So,
But
we don't
so the
care about
instant
what
it
is happening
propagates
outside.
out, the non-acceleration theorem is not going to hold anymore, right? Because let's say there's this one last transect, vertical transect within the eddy, and then you're coming out and you're going to a region where U is now different. The mean flow U is now different. So the interaction would be different. So as you go through this, wouldn't you be consistently losing or gaining energy as an average over the...
For the mean flow is stationary anyways.
No, so basically your wave is interacting with the mean flow with the argument that you show, right? Like if the wave action is conserved, then the energy must change. So all I'm saying is that if, as it reflects, it's going out of the domain where the mean flow has constant properties, it's leaving the eddy and going somewhere else, then won't there be, in a long time average, won't there be an energy change that accelerates or decelerates the mean flow? Simply because you're leaving the eddy. So
Yeah.
do you get what I'm saying?
I'm not sure. But I mean, the thing is, I mean, we have the same simulation with cyclic boundaries. Then I guess all of these wouldn't be a problem.
Probably not, yeah, because you...
And they still show the same thing.
Okay.
I can show you later. We can talk more
Sure.
about it.
Sounds good.
Yes, are there more questions?
I guess first I'll have a comment that the ray tracing approach, even though theoretically it's limited by this scale separation, in practice it works really well, even when you have no scale separation. So that's one comment. I had a question about how you computed your vertical diffusivity. Yes, maybe I missed that.
There you go. There you go.
Yeah.
Here, this is the equation.
Okay.
So it's just the Osborne-Cox relation.
Yeah.
And these Fs are these fluxes of energy going out of phase space.
Okay. Okay, I missed that entirely. So thanks.
I went too quickly through it.
Yes, there's another question.
Thanks. Really interesting stuff here. And I'm sorry I missed Carson's talk the other day. So you started with a Garrett-Monk spectrum, and then the spectrum is evolving. Is there an easy way, or have you looked for a simple way to describe just how the wave spectrum is evolving? Say just the vertical wave number spectrum that might be able to be compared with observations, which I'll be talking about later.
An easy way to compare it.
So there's a typical, there have been examples of variable level Garrett-Monk spectrum analysis of profiling observations, and that might be a way to kind of look for the evidence of the kind of the wave number transformations that you're, of the kind you're seeing.
Yeah, maybe you can point me towards some literature. I would be interested to compare further my results.
I mean, yeah, I guess ultimately you'd want to see what the energy flux in the spectrum is and try to estimate the diffusivities that way.
Yes.
But if there's a way to look at it by level instead of actually computing the flux in the spectral space, that would be
I mean,
a simpler way.
I guess it's similar to what we tried to do with, because the mooring was covering only a part of the whole water column. It was like around 1,500 meters in the upper ocean. And those are the energy levels that we are comparing. Maybe if we would have more observations, we could compare more.
Yeah, and I guess spectral shape as well, if there's something about
yeah.
Okay, so one more quick question.
Hi, Pablo. So did someone just say, so in your model, do you get reflection?
Yes.
Then, okay, so the question would be, can you get over reflection?
What do you mean with over?
So there is so this is more a shift. I mean, so there's the idea in shift flows before where you have a wave which is extracting energy by bouncing off the mean flow, and then that takes energy. If you've got 2 bits where it can keep bouncing off, then every pi will keep taking energy, and then your wave your wave energy essentially explodes. I just wonder if in this case you get something analogous to that.
But then if they are bouncing back and forth, they are losing energy and then gaining energy, so it would be...
So I guess the question is, are there cases where you could, in principle, gain energy on both sides? So you're perpetually extracting energy from mean flow. So in the shear flow literature, that's one explanation back in, I think by Linson, as an explanation for shear instabilities. When you have a jet, you essentially have a wave just that keeps bouncing back and forth. And that ends up extracting energy from the mean flow.
Okay, I wasn't aware from that. Yeah, maybe we can. You can tell me where to read that. I didn't know about that issue.
Okay, then let's thank Pablo once again.